showing the second part. That was only A part 1. A classical wave explanation fails to explain the experimental results of the photoelectric effect. Discuss this statement. Well, this is really well, it was not Einstein getting at this, because this was known about before Einstein, and there was a big problem here with the photoelectric effect. How on earth could a wave picture explain what was happening? So, remember the question is talking about problems with the wave picture applied to photoelectric effect. So it's not talking about give the explanation that Einstein did of the photoelectric effect. It's something slightly different, this question. Is saying how does the wave nature fail to explain the photoelectric effect? Well, okay, so what's the wave picture? Well, light is a wave. The amount of energy carried by the wave is proportional to the amplitude of the wave squared, but energy depends on wave amplitude. But key things of the photoelectric effect are that one is this cutoff frequency. There exists a frequency such that it doesn't matter how bright your source is, you do not get any electrons. So a bright light, a bright source with F smaller than F cutoff gives no electrons. But the wave picture says, well, you know, the brighter the source, the more the energy, therefore you should have plenty of energy to give you electrons. So wave picture implies turn up the intensity, you get more electrons, more energy. So there's a problem there. Photoelectric effect. Every specific frequency gives you a very specific kinetic energy of the electrons. Again, the wave picture doesn't provide any mechanism for doing that. So a specific frequency gives a specific kinetic energy. Wave picture has no way of doing this. What other things? Oh, we can go to really, really low intensity light. So if we're out here, so this frequency here, and we really, really turn down the intensity, and actually we've got a setup in one of our labs where we can do that. We can make this a really phenomenally dim source. We still get photons, still get electrons emitted. So photoelectric effect, a very dim source still gives electrons, whereas the wave picture says, well, you should be able to dim down the source and there's virtually no energy coming in there at all. So it still gives electrons of same energy, you know, of the specific energy. The other thing is that, related to that, the wave thing would say that if you've got a very weak source, then, and it's not given very much energy at all, then to get enough energy from an electron to get out of the atom to overcome that work function, then you need to apply it for a certain period of time. You know, it could take, you know, a second or a millisecond before that wave is able to give enough energy to get an electron out. But in practice, electrons can come out instantaneously. Electrons in the photoelectric effect can be emitted as soon as light comes on. But wave picture says there could be a delay with a weak source, so we need to build up the energy. Questions saying, discuss the statement. Well, you know, this was known, this is what the historical issue was with the photoelectric effect. This is why Einstein's explanation was so powerful, but it really addressed one of the key long-standing problems in physics. Do I get that?
Oh, that's brilliant, yeah.
Yeah. Worth knowing, well, I mean, the question doesn't ask for it, but when we talk about photoelectric effect, remember Einstein didn't discover the photoelectric effect. That was discovered sometime before Einstein. But what Einstein did was provide that explanation for those experimental results.